Swayam Prabha. Digital India. Educated India.
A very warm welcome to this new NPTEL course, Fundamentals of Supersonic and Hypersonic Flow. In the first lecture, we will be talking about introduction to supersonic and hypersonic flow. The concepts that we plan to cover include definitions of supersonic and hypersonic flows, compressibility and compressible flow, definition of Mach number, transition from supersonic to hypersonic flow. Let me introduce the team that will be conducting this course. I am the course teacher Dr. Arnab Roy, Professor, Department of Aerospace Engineering, IIT Khanpur, very ably supported by my teaching assistants Mr. Ribhu Pal, who is a PhD research scholar and Prime Minister Research Fellow at my department, along with Mr. Nitin Krishnan, who is also a PhD research scholar at my department. Let us begin by posing this question that what is supersonic flow? And then if we want to answer it appropriately, we have to answer a more fundamental question, which is that what is compressible flow to begin with. In order to answer this question, we would like to say that a flow in which change of density is significant and it is associated with pressure change, which could also be quite significant. This causes creation of both compression waves, which could be weaker pressure waves called as acoustic waves, and stronger ones which are called as shock waves, as well as expansion waves. Large amount of pressure change is associated with the large kinetic energy content of the flow in all kinds of compressible flows that we can think of, covering the supersonic to hypersonic regimes, where the speed of the flow is above the sonic speed, as well as flows which occur at sonic speeds and at speeds little lower than that in the subsonic regime. All that comes under the purview of compressible flow. You can also have compressible fluid confined within a space where there is no flow as such, but there is definitely compressibility of the medium. Like you can think about the way the air along with fuel mixed with it gets compressed in a cylinder piston configuration that we see in our internal combustion engines. So, there also the gas is actually getting compressed, but there is no significant bulk flow, and therefore, we do not categorize that as a compressible flow as such, but most of the flows that we see at high speeds in the aerospace domain involve large flow velocities in a bulk sense, and therefore, they are categorized as compressible flows. We will spend a little more time answering another question, that what is acoustic speed. This is a very important question to answer, and the answer to that is the speed at which weak pressure waves travel through the medium is called as acoustic speed. These pressure waves carry the information of the flow field and they spread it all over the domain at acoustic speed. Now, how does this information propagation happen? It happens essentially through molecular collisions. So, if you look deep inside the medium, it is comprised of a very large number of molecules which are in a state of continuous motion. They are colliding with each other and colliding with obstacles in the flow and so on, and the information propagation happens within the flow through these molecular collisions. Based on this concept, Could you guess that for which medium acoustic speed will be more if you compare between a solid, liquid and gaseous media, and also explain why it is so. So, this is a small homework question for you to work on. Let us try to answer the next question, that what happens when an obstacle is placed in a supersonic flow. The fluid particles that collide with the obstacle spread out the information through molecular collisions. So, you can see in the diagram below that there is a rectangular obstacle placed in a flow, and the dots are essentially representing some of the gas molecules which surround the obstacle, and these fluid particles are colliding with this obstacle which is placed in the flow. Pressure waves are formed due to this information propagation which move in all directions, but most importantly they move upstream at the local acoustic speed. And why we say most importantly is because these molecules which move upstream would end up interacting significantly with the incoming flow, which also comprises of a large number of particles. The acoustic speed depends on the temperature of the gas, as that dominates the translational motion of the molecules. Now, when this upstream moving wave front meets the downstream moving supersonic flow, and we say that the flow velocity capital U is greater than A being the acoustic speed, the pressure waves tend to coalesce and create a strong compression wave, and that strong compression wave is essentially the shock wave that we talk about, and it lies somewhere ahead of the body. Now, in a supersonic flow, the flow speed is always greater than the acoustic speed. This is one of the things that we have to keep in mind, that the capital U, which represents the flow speed, is greater than A, which is the acoustic speed. The distance ahead of the body where the shock is formed is called as shock standoff distance. Now, at this point it may be intuitive to imagine that the higher the U with respect to A, lower would be the shock standoff distance. That means higher the flow speed gets, the closer the shock stands ahead of the body. Now, we talked about a bow shock here because the shape of the shock wave that we see over here essentially looks more like a bow. Let us talk briefly about compressibility effects. So, we will represent compressibility through a nomenclature tau suffix beta, and this will essentially tell you about the fractional change of specific volume of a fluid element due to high applied pressure change. Inverse of compressibility is known as bulk modulus, which is denoted by K. Now, if you look at the equation in the green box, then you see that tau suffix beta is given by minus 1 by small v del P, and here the small v represents the specific volume of the fluid. So, it is the volume of the fluid per unit mass, and then you take a partial derivative of the v with respect to P, and if you can imagine that you are compressing the volume of a gas of a certain mass, then the volume change is negative. So, the actual volume V is positive, but del V del P will turn out to be negative, because if you increase the pressure, which means the delta P is positive, then you will have a decrease in volume, which means the delta V will be negative, and therefore, a negative value of the derivative will be multiplied with the minus 1 by V, giving you finally a positive value of tau beta. If you look at it from the point of view of density, then the connection between small v and density is the small v is equal to 1 by rho, and then you will find that if there is a positive change in pressure, there is also a positive change in density. That means, if you impose an increased pressure on the gas, then it gets squeezed within a smaller volume, and then essentially its density increases because the mass remains invariant. The same mass gets confined within a smaller volume, and therefore the density increases. And you will find that if you replace V by 1 by rho, then tau beta will be given by 1 by rho times del rho del P. If you move on to the red box, then tau beta is given by 1 by rho del P, which is equal to 1 by rho A square, which basically means that the value of the del rho del P is given by 1 by A square. So, you may try to look up your earlier course lessons of compressible flow and then try to figure out how we can replace that derivative by 1 by A square. So, that is another small homework problem for you. We move on to another very important topic which will remain with us all through the course, that is Mach number. Mach number is a non-dimensional number of enormous relevance in compressible flows, and it tells you about the domination of fluid particle inertia force over elastic force. Elastic force of fluid flow is responsible for propagation of pressure waves across the medium through the molecular collisions. So, the definition of Mach number given by capital M is under root inertia force by elastic force, and then inertia force is represented in terms of the density times area times square of the velocity, and the elastic force is represented as a product of K and A. And then if you try to replace K by rho times del P del rho, which is based on the discussion that we had regarding tau beta and the fact that K is inverse of tau beta, then you find that the expression basically simplifies to under root U square by A square, and then we essentially simplify it further and write it as U by A. So, this is how the representation of Mach number looks, and though the foundation of the Mach number concept lies in the ratio of the inertia force and elastic force, when we try to put in the expressions and we come up with the final answer seems to be a very simple one. It is basically a scaling between the flow velocity and the acoustic velocity. So, this is another very important term that you should always remember. We earlier asked the question that what is supersonic flow, and in this course, since we are going to study both supersonic as well as hypersonic flows, we come up with this next question, that what is hypersonic flow, and let us try to answer that question. Hypersonic flow is essentially the gateway from aeronautics to astronautics. So, if you look at the diagram here, on the left you see typical applications that we see in the supersonic flow regimes, which we generally refer to as aeronautics applications. Most of these applications occur within the atmosphere surrounding the earth at comparatively lower altitudes and at comparatively lower speeds compared to the hypersonic regime. So, we typically talk about supersonic Mach numbers, where the Mach number values may be going beyond 1 to values of 2, 3 onwards. And then here in this picture we typically see two fighter aircrafts moving through the Earth's atmosphere, and they are moving in a staggered manner, and you can find that there seem to be pressure ripples formed around them, which are essentially a collection, a very complex collection of compressive as well as expansive waves. You are also able to see the jet plumes behind the aircrafts, and interaction of these wave patterns in the sense that the wave patterns which one aircraft creates, they can travel to far off distances, and these waves can also impinge on the waves formed by another aircraft in proximity or on the other aircraft itself, and therefore a lot of interactions between these waves are possible. And as I already said, that some of these waves are of the compressive kind, some of them are of the expansive kind. It depends on the flow geometry, how the flow velocity moves across the different portion of the aircraft geometry. Accordingly, the waves are formed around the bodies. So, this is something that we can relate rather easily, because we do see some of these flows around us quite often. And then comes the hypersonic regime, where essentially we are talking about higher end Mach numbers of the supersonic regime. We do not try quantifying the Mach number ranges as such, but we will later see that we can quantify them by using more important guidelines which drive the differences in the flow field character, the nature of the flow field, which starts differing as the Mach numbers become higher, and that is how we try to get into the hypersonic regime, which is the really high supersonic regime, where in a subsequent slide you will see the kind of changes in the flow field that we are talking about, the flow character that we are talking about more specifically enlisted. And then very high Mach numbers, which are at the higher end of the hypersonic regime and beyond, are essentially categorized as the hypervelocity regime, and that falls into the domain of astronautics, where we are talking about the very high enthalpy flows which are used to distinguish those flows in which velocity is so large that the conditions which occur across the shocks which are formed on bodies which are exposed to such flows cause the molecular components of the gas to dissociate. So, there is dissociation, there is further ionization of the medium. So, hypervelocity flows are extremely high speed flows which even go beyond the hypersonic regime, and they fall in the domain of astronautics. So, hypersonics seems to be lying in the intersection between aeronautics and astronautics applications. The transition from supersonic to hypersonic flow, if we were to try categorizing this, which we were trying to address kind of intuitively in the previous slide, is that in compressible flows there will be an interaction between kinetic energy and internal energy of fluid particles. When the interaction is large, it can cause the excitation of vibrational energy modes, dissociation, recombination, chemical reactions, and even ionization of fluid molecules. Then the flow is said to be hypersonic. The ionization part, though, will strictly be categorized more as a hypervelocity flow. So, we find that first of all there is excitation of vibrational energy mode, which we do not see at the lower supersonic Mach numbers. We are talking about dissociation of the gas molecules. We are talking about recombination of dissociated atoms. We are talking about chemical reactions due to the extremely high temperatures which exist in such flows. So, there are a lot of changes which are coming up in the flow field which help us to distinguish it from a typical supersonic flow. So, these are the kind of changes that we were talking about in the last slide, which we are trying to more emphatically present over here. And we say that this parameter beta, which is the ratio of kinetic energy by internal energy, plays a major role in distinguishing these flow fields. How do we distinguish between supersonic and hypersonic flow? one of the ways we can go about doing it is trying to track how beta behaves. So, if you look at the individual expressions, then you will find that it's given by half of mu square by capital E, and capital E is further broken down into the mass times specific internal energy, and then that is replaced by the product of CV times T. So, that is specific heat at constant volume CV that we see over there, and then finally, if you simplify this expression further, you will be able to show that it is equal to gamma by 2 into gamma minus 1 in brackets times m square, which is the square of the Mach number. So, gamma being the ratio of Cp by Cv. So, how to prove this equation that we finally get for beta in terms of gamma and Mach number of the flow is left as a homework exercise for you. When beta increases from small to large values, then we see changes occurring in the medium, changes occurring in the flow, and this is something that we have started talking about since the last 2 or 3 slides. We see at the supersonic regime excitation of both translational and rotational energy modes within the molecules, but vibrational energy mode is not excited in that state. However, as we move from the supersonic to hypersonic regime, we see excitation of vibrational energy modes, and then gradually at the higher hypersonic Mach numbers, dissociation, recombination and associated chemical reactions occur, and some of these phenomena may be occurring at equilibrium conditions, while others may not be working at equilibrium conditions, and then we have to account for non-equilibrium effects. Further, excitation of electronic energy modes causing ionization is something that is going to occur at the intersection of hypersonic and hypervelocity flow regimes. So, when the flow turns gradually from hypersonic to hypervelocity, then we see that the gaseous medium starts showing the effect of ionization. That means formation of plasma. Now, the word hypervelocity is helps us to classify based on the velocity ranges that we are talking about. The word astronautics helps us to classify based on the application. So, that was a very introductory discussion on supersonic and hypersonic flow and different aspects that encompass these 2 flow regimes. We now gradually come to 2 important references which may be useful for you to go through and read as you cover the course. So, the 2 references happen to be Fundamentals of Compressible Flow by Brian J. Cantwell, which has been published recently, and Modern Compressible Flow by J.D. Anderson Jr., which has been around for quite some time, and these are both going to be very important references for you. And as we move along the course, we will talk about more references which are appropriate for other sections of the course. We now conclude by saying that we initiated a discussion on the introduction to supersonic and hypersonic flows in this lecture. Some of the fundamental concepts like compressible flow, compressibility, acoustic speed versus flow speed, Mach number, the supersonic to hypervelocity speed regime changes, trying to identify the characteristics of different speed regimes, and the associated changes which happen within the molecular levels were briefly discussed and introduced in this lecture. Now, these concepts will be expanded further in much greater details in the subsequent lectures as we move along with the later lectures of the course. So, with this we come to the end of the first lecture of this new NPTEL course, and I sincerely thank you all for your overwhelming response in joining us and enjoying this course. Thank you.